Hey everyone, we'll start in a few minutes. Uh, Whoever is starting first, you can your screen share.
Adish, can you make me the co-host so I can share?
You can share now. I mean, yeah. Can you try share?
Okay.
Hey guys, am I audible?
Yeah.
Yeah.
Yeah, okay then. So are you all ready with the today's topic?
Yeah.
Okay, so can you all who are presenting today? It is Kushal and who is that? Kushal and
Vaishnavi.
Vaishnavi and
He's the Yuang and Akshit Maratha. 5 people are presented.
5 people.
Hmm.
Okay. Will Kushal be sharing the screen throughout or will the screen shares be changing?
No,
Yeah,
each will be
we'll
sharing
be.
their own.
Yeah.
Okay. So you can start, Kushal.
Okay, so I can start, right?
Yeah.
Okay. Hey guys, good evening. So today the second day of the lecture series, and it's gonna be about astrophysical and cosmic neutrinos. So we are gonna begin with Big Bang neutrinos, but before that, let's start with why Big Bang neutrinos. So I'm gonna give a brief through the history, and Vaishnavi is gonna take up from there. So first, why did Big Bang produce something rather than nothing? We all know it started from a singularity, right? So, okay. Part of the blame or the glory, they say, may belong to the quickest and the most elusive elements of nature, neutrinos. These ghostly subatomic particles stream from the Big Bang, the sun, exploding stars, and other cosmic catastrophes, flooding the universe and slipping through the walls and our bodies by billions every second. Neutrinos are escape artists. Did they help us slip out of the Big Bang? Recent experiments in Japan have discovered a telltale anomaly in the behavior of neutrinos, and the results suggest that amid the theories of creation and annihilation in the first moments of the universe, these particles could have tipped the balance between matter and its evil twin opposite antimatter. As a result, started out with a clean balance sheet, equal amounts of matter and antimatter, owned up with an excess of matter, stars, black holes, oceans, and us. In the perfect universe, we do not exist. So, according to the dictates of Einstein relativity and baffling laws of quantum theory, equal number of particles and their opposite antiparticles should have been created in the Big Bang. that set the cosmos in motion. But when matter and antimatter meet, they annihilate each other, producing pure energy. Therefore, the universe should be empty of matter. That didn't quite happen. And of the original population of protons and electrons in the universe, roughly only are particles in a billion that survived the first few seconds of creation. That was enough to populate all the things you see in the space right now, the stars, the planets, and all the human beings on Earth. So, to understand this, we need to take the help from the ghost side, which is neutrinos. Neutrinos would seem the excuse of what base to our base of existence, the most tiny quantity of reality ever imagined by a human being. A phrase ascribed to the Frederick Rains of the University of California, who discovered neutrinos. They entered the world stage in 1930 when the theorist Wolfgang Pauli postulated their existence to explain the small amount of energy that goes missing when radioactive decay spits out an electron. Enrico Fermi, the Italian physicist, gave them their name, Little Neutral One, returning to their lack of referring to their lack of an electric charge. Second to photons, which compose of electromagnetic radiation, neutrinos are the most plentiful subatomic particles in the universe for their ability through ordinary matter like ghost. They are so light that yet to be weighed in reality. But that this is just the beginning of an ephemeral magic. The idea of Big Bang that our current universe expands from a point of incredible heat and density has ever been spreading and cooling. One way is to look at the kind of light is the cosmic microwave background. But this light emerges only around 4,000 years after the Big Bang took place. It took quite a while of slew of matter to combine enough so that light could actually travel outward rather than being trapped in opaqueness. So Big Bang neutrinos and the cosmic microwave background will be continued by Vaishnav. Thank you.
Sagar, I need to share. Okay, thank you. Is it visible?
Yes, yes, it's visible. Okay, so am I audible?
Yeah, Vaishnavi, go on.
Okay, so before we go into Big Bang neutrinos, could you go to the next slide, please? Okay, so before we go into the Big Bang neutrinos, let's see what is cosmic neutrino background, CNB. So they are universe's background particle radiation composed of neutrino. Similar to the CMB, that is cosmic microwave background, the CNB was induced around 2 seconds after the Big Bang. Unlike CMB, it has been theorized but dismissed and hasn't been detected yet. The CNB has temperature of roughly 1.95 Kelvin and the energy around 10 to the power minus 4 to 10 to the power minus 6 electron volt. And they remain undetected due to the low energy. However, some effects of relic neutrinos can be seen in data collected by telescopes such as Planck or BICEP. Also, experiments such as Ptolemy can help us measure the mass of the Big Bang neutrinos. Next slide, please. Now we have learned about CMB, so let's take a look at Big Bang neutrinos. There are several sources of neutrinos, and one of the oldest known to us is Big Bang. The timeline of a neutrino can be traced back to 10 to the power minus 4 seconds after the Big Bang. These first created neutrinos are known as relic neutrinos. After 1 second of the Big Bang, the universe became transparent to neutrino and allowed them to travel freely through the space. Next slide, please. Now, one may ask, why is it important to study these relic neutrinos? We know that CMB, that is cosmic microwave background, is oldest kind of light. but it emerged only after 400,000 years of the Big Bang, whereas neutrinos and antineutrinos from a second after Big Bang are theorized to be still remaining out in universe as they stopped interacting when the universe was just 1 second old. So studying these neutrinos could provide us earliest insight into our history. Next slide, please. Now let's take a look at another important topic, which is Big Bang nucleosynthesis. It is the production of nuclei other than those of lightest isotope of hydrogen. It started roughly 10 seconds to 20 minutes after the Big Bang. One of the important parameter of it was neutron to proton ratio. An asymmetry between neutrino and antineutrino has direct effect on BBM, that is Big Bang nucleosynthesis, through the charge current peak interaction, which regulates the neutron to proton ratio. At times, much earlier than 1 second, these reactions were fast and maintained the neutron to proton ratio close to 1:1. As the temperature dropped, the equilibrium shifted in favor of protons due to their slightly lower mass, and neutron to proton ratio decreased. Next slide, please. So neutrinos, they're scattered by interaction between electron and positron as the reaction given below. After that, neutrinos stopped interacting with other type of matter and ceased to influence dynamics of universe. Decoupling of neutrino took place approximately 1 second after the Big Bang. Now that we have learned about CNB and Big Bang neutrino, I wanted to speak a little about Ptolemy. Next slide, please. The Big Bang neutrino are believed to be abundant in the universe, estimating 300 Big Bang neutrino in every centimeter cube. But due to their low energy, it's difficult to detect them. Ptolemy stands for Princeton Tritium Observatory for Light Early Universe Massive Neutrino Yield. Its aim is to achieve sensitivity required to detect the relic neutrino background. It is designed for neutrino mass detection, and Ptolemy approach to detect CNB. It exploits the neutrino capture process on beta minus unstable nuclei, like the one with tritium. So that was all about Big Bang neutrino. Now let us see stellar neutrino.
Okay, let me show you the path through stellar neutrinos, the reaction and all. Okay, so I will be presenting using a LaTeX. So hope you are comfortable with it. So let's start with stellar neutrinos. But before going through the reactions, I wanted to make you understand what is a nucleosynthesis, or more detailedly, what is a stellar nucleosynthesis. So basically, it is a process of creation of elements through nuclear reaction, basically fusion reactions, which happens in stars. This process actually, that nucleosynthesis process actually began at the time of Big Bang only, when elements such as hydrogen, helium, and lithium were created. And it tells us about why element is more abundant than other elements and why the abundance of elements changes over time. So stars majorly, they majorly begin by fusing hydrogen in its core, and those stars are called main sequence star. Then they fuse helium, and those are called horizontal branch stars due to HR diagram. And similarly, they form other heavy elements according to the mass of the star. Heavy elements such as like carbon, nitrogen, silicon are they are formed by gravitational collapse, and we will go I will tell you how they are formed. And the heavy elements, then iron, since iron is more stable element, the star doesn't form any heavier element than iron, but it can be formed when a supernova happens. So when a supernova happens, the core collapses, the upper layer collapses into the core, which create a very big shock wave, and it actually increases the temperature of the star by, you say, 50% of its initial temperature. And at that time, those fusions are known as supernova nucleosynthesis. And of course, the neutrino is released as a byproduct of all these fusion reaction happening. So let's start with hydrogen fusion, how neutrinos are released when hydrogen fuse. So basically there are two ways the hydrogen fusion occurs. The first is a proton-proton chain reaction and other is CNO cycle, which we studied yesterday. So I'll be like going in detail of proton-proton chain, and since we have studied CNO cycle before, I will not be going in depth of that. So a proton-proton chain, it is commonly known, also known as PP chain, is actually a major process which form hydrogen to helium. It is very dominant in stars which have mass less than or equal to our sun. For this reaction to occur, like consider two hydrogen atoms, and for them to combine, they have to overcome the electrostatic repulsion of the electrons. So they should have enough kinetic energy to overcome that. So they need a certain temperature to overcome these reactions. Also, let's see the reaction. Okay, so you can see here the proton and a proton react to form a deuterium, and a positron and antineutrino is released. Electron antineutrino specifically is released, and that positron which is released, it gets annihilated by an electron, which in turn produces two gamma rays. So how does this happen? So in these two protons, actually one proton goes under a beta plus decay, which forms a neutron for the deuterium. And as a result, it releases an electron antineutrino. After this, the deuterium reacts to, like you can see here, it reacts with proton to form helium-3 and releasing gamma ray and all. One thing to note is that this reaction, or you can say this process, is very fast. Like it happens in just a second. So like it doesn't, like the deuterium doesn't last longer than 1 second in the core of the stars. It directly converts into the helium. After the helium-3 is formed, actually it can be like heavier elements can be formed with four processes, and those four processes are like they made into branch, and let's see what first branch goes through. So the first branch, two helium-3 atoms simply combines to form a alpha particle and two protons. You can see two hydrogen atoms. Okay, that's simple. And the releases an energy of something about 12.859 mega electron volt. Okay, we got that also. But it is here written that the total energy released by the complete chain in this process is this much, which is 26.732 mega electron volt, where 2.2% is lost through neutrino. So where was the neutrino? Let's see it again. So here is the neutrino. So we can calculate the energy of neutrino by adding these two these two energies and subtracting it from the total net energy of the process. The PP1 branch is actually occurs at a temperature of around 10 to 14 mega kelvins. Let's go to the second branch. Second branch is also simple. After the formation of alpha particle in the first branch, the alpha particle reacts with the helium-3 particle to form a beryllium-7, which in turn emits a gamma ray and then energy, of course. And that beryllium then reacts with an electron to form a lithium minus ion, which is a sort of unstable, because then it reacts with a hydrogen and form two alpha particles. So in terms of one alpha particle is reacted and two alpha particles are being produced here. Also, you can notice that I have put a slash here. So this slash actually represents, like, okay, let me explain you. In this reaction, the 0.861 mega electron energies are carried by 90% of the neutrino, but those 10% of the neutrino carry 0.38 mega electron volts energy. So this is why I've put a slash here. Let's go to the third branch reaction. So in this also, it is similar to second branch reaction. The first process, like the alpha particle will be reacted with helium-3 particle to form a beryllium. But after that, the beryllium doesn't react with an electron. As you can see here, it reacts with an electron. But in PP3 branch, it reacts with a proton, which forms a boron 8, and gamma ray is produced. And that boron is like decayed into a beryllium, which in turn produces neutrino. So our major goal is to like study the neutrino reaction. So yeah, And that beryllium is further decayed into helium. That's okay, yeah. After that, there is also a fourth reaction called a PP4 branch and HEP, because helium proton interaction. As you can see here, we have studied that helium has directly reacted with the alpha particle or helium 4. But here the helium 3 particle reacts with a proton, or you can say a hydrogen atom, to directly form a alpha particle or helium 4, and in turn releases a neutrino and a positron. Actually, this reaction is purely theoretical. It is very, very rare to happen, and I will show you the probability of these reactions to happen. As you can see that I've written in short that since neutrinos react with very less matter, they don't heat up the interior of the sun, which like helps it resist the gravitational collapse. The energy is lost, like you can see in PP1, they take away 2% of the energy of the total net reaction. And in PP2, they take away 4%. And in PP3, 28.33% of the energy is lost due to neutrinos. There is a second type of reaction, third type of reaction, that is known as proton-electron-proton chain, which is also quite rare to happen. But it happens, and we can detect it because the neutrino released during this process is of very, very high energy. So yeah, we can detect a high energy anti-neutrino very easily. Okay, a electron neutrino very easily. Yeah, sorry. And here you can see a schematic like diagram, or you can see a flow chart of the proton-proton chain reaction. The majority probability, these are the probabilities written here for the particular reactions to happen. As you can see, we have read proton-electron-proton reaction here, PEP chain reaction. Its probability is 0.24%, and it's detectable. It's quite rare, but it's detectable. These two reactions form, as you can see, helium-3 and releases a gamma ray, which in turn goes through 3 different processes. As you can see, I have written which branch the process is and their probability with them. And what we need to notice is here, this part. This part is when helium-3 is directly reacting with a proton to form a helium-4. And I told you it is quite rare event, and its probability is 2 into 10 power minus 5%. So it has not been detected yet. Now let's come to the helium fusion. So a helium fusion, it's quite simple. It occurs in like 2 processes. One is triple alpha and other one is alpha. So in triple alpha processes, 3 helium or 3 alpha particles converts to carbon, and it's quite easy. You can see that 2 helium particles interact to form a beryllium, and it's an endothermic process. And then beryllium reacts with another helium to form a carbon. So yeah, these are quite easy, and the net energy release is this much, 7.275 mega electron volt. And this is a schematic representation of, you can say, an overview of triple alpha process. 2 helium forms a beryllium, and that beryllium reacts with a helium to form a carbon. It's quite simple. The next is a normal alpha process, and it is also known as alpha ladder. As you can see, there are many reactions here, but they are very easy. Let's start the reaction starts with carbon interacting with a helium, which forms oxygen. Then its product is taken as a reactant for the next reaction to happen, and then alpha particle reacts with that to form another particle. So these are a type of a ladder going through. As you can see, that's why it is known as alpha ladder reaction also. And yeah, it's quite easy to happen. And this can happen till helium fusion happens till nickel. Okay, I've written that there is a misconception here that the alpha particle, that alpha process stops at like nickel. Most people think that it stops because nickel is a stable nuclide, but the real reason is that the condition inside the stellar jet core is such that there are 2 processes known as photo disintegration and alpha process. So the condition inside the core is such that it favors of the photo integration or disintegration of the iron, which lead to more of nickel 56 than nickel 62. So this is the real reason why the alpha process stops at that point. And this is the summary of all the hydrogen and helium. As you can see, alpha process is quite simple to represent also. It kind of like Ferris wheel. Yeah. The next process is known as lithium burning, and this we will not go into detail, and yeah, because it has not been studied that much. But the main thing is it is commonly found in brown dwarf stars, and these are basically proton-proton chain reactions, and they are particularly named lithium burning because lithium is used in these reactions. And you can see we have studied this reaction, and it results in the formation of electron neutrino. The next is the carbon fusion reaction. Again, this is an important reaction because at this point, you will not see any neutrino released in these reaction directly. And we will come to that why the neutrino is not released directly when the carbon fusion and upper fusion of elements. So basically the temperature for it to occur is 5 into 10 power 8 Kelvin. And these are also quite simple. I'm sorry, there should be a C here, but yeah. 2 carbon interacts with to form sometimes neon, sometimes sodium, and sometimes magnesium. And some alternate happens like sometimes it forms a magnesium 23 and sometimes it forms a magnesium 24. So these are quite simple reactions. Same happens with the neon. You can see the temperature for neon fusion, and then you can see the reaction. You will not notice any neutrino released here. Same goes with the oxygen fusion. And for our main aim is to like study the formation of neutrino. So these are basically a reaction for us. Like you can remember it, but it will it's up to you. And same goes with the silicon fusion. The main topic we have to come is through neutrino loss. So since there is no direct release of neutrino, how do these stars produce neutrino? That's the main question, right? So this process is known as actually a neutrino loss, and it happens in stars which like after they start fusing carbon, because at that time they need a higher temperature and it occurs only in higher temperature. So the basic idea is that the neutrino is released using a process called a pair production process, which is in quantum theory. And it's very easy to understand. High energy gamma ray, as you can see, the gamma ray are released in many steps. You can always see gamma ray everywhere. So that gamma ray has to be has an energy more than or equal to rest mass of 2 electrons. So you take the rest mass of 2 electrons and convert it into the energy using E is equals to mc square. And if the energy is greater than if the energy of gamma ray is greater than that energy, it reacts with electromagnetic field to form a particle and antiparticle pair. Okay, I think you got the basic idea. These basically normally when the particle and an antiparticle happens, everyone have studied that in Big Bang, electron and positron annihilated each other to form a photons. This actually it happens, but it only happens at a lower temperature. When you come at a higher temperature, you will notice that also in Big Bang neutrinos, that if there are 10 power 9 pair production happening, then in one of it, they will react with weak forces using W bosons. Actually, they will not directly annihilate each other. The electron and the positron will react with the weak forces, which will produce neutrino and antineutrino pair simply. And these neutrino are they have very high velocity, comparable to speed of light, and they just went whoosh. So easy to understand that. And they don't interact with anything like that, matter. And yeah, and when you calculate those energy of neutrinos, you will find that they are very comparable to the energy released in the fusion process. And this neutrino loss actually plays a major important role in massive stars, because they force the star to burn its fuel at higher temperature to offset them. So yeah, the last line is you will not notice them till helium fusion, but it becomes a very major process after carbon fusion. So this is all about stellar neutrinos. Now my friend will go into detail about supernova neutrinos. Thank you.
Thank you, Akshat. Am I audible?
Yeah, bro.
Okay. Can you see my screen?
Yes.
Okay, so I'll be talking about supernova neutrinos. Okay, so before starting with supernova neutrinos, let's just discuss about what is supernova. So when a massive star, by massive star I mean a star whose mass is greater than 8 solar masses. Okay, so when a massive star runs out of its fuel, then the core of star starts to collapse under its own gravity, and this results in an immense shock wave. And this shock wave gives rise to a huge luminous explosion known as supernova. So the neutrinos formed during a supernova are known as supernova neutrinos. And about 10 to power 52 neutrinos and antineutrinos of all atomic flavors are emitted by the supernova. And these neutrinos carries about 99% of the total energy of this dying star. And the average energy of neutrinos is between 10 to 20 mega electron volt. That is why supernova are considered to be the strongest and the most frequent source for cosmic neutrinos in mega electron volt energy range. Since neutrinos are generated in the core of supernova, so they play a crucial role in the star's collapse and explosion. So, by observation of neutrinos, basically, we get a lot of information about the supernova itself, about its core collapse and its explosion mechanism. And further, in the supernova's dense interior core, there is okay. We can okay, wait. We can study neutrino-neutrino interaction more better. Let's move to the production of neutrinos inside the core. Okay. Supernovas neutrinos are produced by massive star. We know that, and when it is at the end of its life, it get converted into a red supergiant, or it may convert into a blue supergiant. It just depends on its mass, the initial mass of the star. So when it is near the end, the massive star, it is basically made up of onion layered shells and with a dense core of iron. And during the early stage of collapse, the electron neutrinos are created through electron capture on proton bound inside the iron nuclei. So what is electron capture? Here is the reaction which happens. So this is a proton. It captures an electron from the nearmost shell. It may be a K or L shell, and it gets converted into a neutron, and thus forming electron neutrino. Here's the Feynman diagram for this process, and here is a diagram of electron capture. Please ignore this positron thing. I'm so sorry for that. So proton captures an electron and then convert into a neutron and releasing an electron neutron. I have a good example of it. Here it is. So it is this is carbon 11, which has 6 protons and 5 neutrons, and it captures an electron. This proton captures an electron and thus convert into a boron 11, which has 6 neutrons and 5 protons. So basically, one proton gets converted into a neutron and thus releasing electron neutrino. So in this above reaction, through this above reaction, what happens is the core became neutron rich nuclei. All the nuclei are neutron rich. Thus, this is also known as neutronization phase. And now some nuclei undergo beta decay and produce anti-electron neutrinos. So this is the reaction here. Okay, this is the Feynman diagram. So it is neutron and it is proton. So the up and down quark of neutron remains the same, and the down quark, one down quark of neutron gets converted into an up quark, thus forming a proton. And this change in the flavor releases a W minus boson, and which later decays to an electron and electron antineutrino. Now, in this above process, basically, I don't know exactly about it, but I think the first electron capture process is happening more than this beta decay. That's why here in this reaction, electron is getting consumed. That's why the electron density inside the core decreases. So electron is a lepton. So The above process reduces the core energy and its lepton density, and hence the electron degeneracy pressure is unable to stabilize the stellar core against the gravitational force. So that's why the star starts to collapse. And when the density when the density of the central region of collapse exceed 10 to power 12 gram per centimeter cube, the diffusion of neutrinos exceeds the collapse time. Therefore, the neutrinos now gets trapped inside the core, and which that's why neutrinos cannot escape the core now at this density. And when the core reaches the density about 10 to power 14 gram per centimeter cube, the nuclear pressure causes collapse to decelerate, and this generate a shock wave in the outer core of the iron core, and which triggers supernova explosion. And now the trapped electron neutrinos inside the core gets released, and this is known as neutrino burst, and it happens in the first tens of milliseconds. Now, it is a simulation. It is found that the neutrino burst and iron photo disintegration. So, what is this photo disintegration? So, it is a nuclear process in which an atomic nuclei absorbs a high energy gamma ray and enters an excited state and immediately decays to emitting a subatomic particle, any subatomic particle. So in this simulation, it was found from the simulation of neutrino burst and iron photo disintegration, it weakens the shock wave within milliseconds of propagation through the iron core. Thus, weakening the shock wave result in mass infall. Therefore, here the gravitational force is dominant. Therefore, it forms a neutron stars. And this is known as acceleration phase and lasts between a few tens to few hundreds of milliseconds. Now we are talking about the neutron stars force. So the high density again traps the neutrinos inside it, and when the temperature reaches 1 mega electron volt, it is about 10 to power 10 kelvins. Then here the thermal photons now decays to an electron and positron pair. So, and this electron positron pair annihilates to form an neutrino and anti-neutrino, and it can be of any leptonic flavor. That's why it is this alpha denotes lepton. It can be of any leptonic flavor. Now here the luminosity of electron flavor is significantly higher than the non-electron ones. It means the electron flavor is abundant in the release of neutrinos, because in the above electron capture and this beta decay, also the electron neutrino and anti-neutrino is released. So the luminosity, it means the electron flavor is basically abundant than the non-electron. So now, as the neutrino temperature rises due to heated core, the neutrinos get energies and thus reacts with the free nucleons. So now the neutrinos reacts with electron neutrino reacts with the neutron, and electron anti-neutrino reacts with the proton, thus giving a proton and electron and positron and neutron respectively. So when the thermal pressure created by the neutrino heating due to the heated core, neutrino and due to when the thermal pressure created by the neutrino heating increases above the pressure of infalling materials, increases, basically it gets greater than gravitational force, then there is a rebirth of a new shock wave, and now again the neutrinos are released, and thus these neutrinos are of very high energy. I told its average energy is between 10 to 20 mega electron volts. So the neutron starts cool down as this pair, and therefore it is known as a cooling phase. And now the luminosity of different neutrino and anti-neutrino species are roughly the same. It means like the flavors of neutrino and anti-neutrino, there's no abundance of any specific flavor. All electron, muon, and tau neutrinos are roughly of the same amount. So now my friend Kirti will continue with her topic. Thank you.
Is my screen visible?
Yes, yes. It is.
Okay. So hey guys, I'll be talking about the cosmic neutrinos. It is the last topic of today's lecture. So let's start with the basics. The neutrinos come in three different flavors, that is the electron neutrino, muon neutrino, and tau neutrino. Because of their extremely weak interaction and being charged neutral, they are the least understood particles among all the elementary particles of the model. Only until the last couple of decades that we recognize that neutrinos actually have a non-zero mass, non-zero rest mass, and they change their flavors back and forth. That is, the electron neutrino can be turned into a muon neutrino and into tau neutrino, which is the neutrino oscillation. The universe is actually filled with the neutrinos. As said before, about billions or trillions of neutrinos are actually passing through our body every second, and they contribute to about 0.3% of the total energy density of the universe. The cosmic neutrinos can be subdivided into cosmic neutrino background, stellar neutrinos, and cosmogenic neutrinos. And the cosmic neutrino backgrounds and stellar neutrinos were already explained before. When we think about the cosmic neutrino background, we think of the cosmic microwave background, which was induced around 380,000 years after the Big Bang. On the other hand, the cosmic neutrino was induced around 2 seconds after the Big Bang, when the rate of their interaction with other particles became slower than the rate of expansion of the universe at that time. It is estimated that by now, the cosmic neutrino background would have also cooled down along with the universe, and its temperature now is 1.9 Kelvin, and their energies are about 10 to the power -4 electron volt, which makes them non-relativistic, and the CNB has never been detected. All stars shine as a result of the nuclear fusion reaction in the stellar core, and one of the necessary product of the nuclear fusion is the electron neutrinos. These being very weakly interacting, these neutrinos escape from the star and they reach the Earth, where we are able to detect them. The neutrino flux from the sun at the Earth is about 10 to the power 11 particles per centimeter square per second. Also, when the star uses up all its nuclear fuel, it explodes in a very beautiful supernova, and it releases a huge number of neutrinos. About 99% of the exploding energy is carried by the neutrinos. Finally, here comes the cosmogenic neutrinos. These are the high energy neutrinos, which I'll be discussing today. The cosmic neutrinos are generated by cosmic rays in extragalactic sources that can be thought as cosmic accelerators. And these neutrinos carry far more energy than any other kind of neutrinos we see here on Earth. So some of the neutrinos we see here on Earth are the atmospheric neutrinos. These are the neutrinos released in the atmosphere. And they have the energy of about 1 to 10 trillion electron volts. And another one is the Large Hadron Collider, which is the largest particle accelerator here on Earth. And these are also can produce neutrinos of energy 13 trillion electron volts. While here, the high energy neutrinos are up to 1,000 trillion electron volts. They are particularly important because they point to an intense event in the cosmos, such as shown in the picture, which is the black hole consuming a stellar remnant. So here you can see that two jets are pointing upwards as well as downwards. And these are the places where the neutrinos will be produced. And these jets are the creation of high energy neutrinos. So this is actually a video of the black hole consuming the stellar remnant, which is a magnetar. It can be a little dramatic, but it is actually worth a watch. Before that, I just wanted to ask, does anyone know what is the name of the central supermassive black hole in our galaxy, Milky Way?
Sagittarius B.
Okay, yeah, it's Sagittarius A actually. Anyway, let's look into the video.
In the center of our galaxy, the Milky Way, there is a supermassive black hole feeding on nearby stars. It's called Sagittarius A star. And if a giant gravitational monster slowly eating the galaxy isn't terrifying enough, there's another cosmic monstrosity lurking around it. Is it possible that one day they would get a little too close and collapse on each other? What would be left of the Milky Way if they did? Would there be even a slight chance that the Earth could get out of that safely? This is What If. And here's what would happen if a magnetar collided with a black hole. This monstrosity creeping through the Milky Way is a remnant of a giant exploded star. But it's not just any remnant. It's an extremely dense and very magnetic collapsed stellar core, a magnetar. Let me refresh your knowledge of magnetars. They're born when a star, at least 8 times more massive than our Sun, reaches its expiration date and explodes in a beautiful supernova. Much of that star is gone, but the dense core of it remains. Most of these remnants become neutron stars. They spin very fast, usually a few times per second, and they're composed of neutrons. Some neutron stars have such strong magnetic fields that they emit electromagnetic radiation from their poles. That makes them pulsars, and you can observe them with a telescope when their poles face the Earth. Only a few pulsars develop such an extremely powerful magnetic field. They become the strongest magnets in the universe, the magnetars. They spin once every 10 seconds, but their magnetic field is 100 times stronger than that of a neutron star. If one of those magnets came halfway between the Moon and the Earth, well, it wouldn't be pretty. But would it be as bad from a distance of 26 light years away? Well, what I'd like to know is, would a magnetar swallow a black hole, or would a black hole gobble up a magnetar? The collision of these two giants wouldn't end up in an explosion, but in a quiet cosmic merger, stretched over billions of years. Although magnetars are incredibly powerful, they would lose the battle with a black hole. Depending on the trajectory of the magnetar, as well as the size and mass of both the magnetar and the black hole, the magnetic monster would be eaten up either whole or slowly, piece by piece. As the magnetar was being torn apart by the black hole, it would be sending gravitational waves throughout the universe, disturbing the curvature of space-time. Once the black hole consumed the magnetar, its mass would increase and expand its event horizon. And thanks to this expansion, more and more stars would be flung into its dark density. The black hole would be slowly eating our galaxy, star by star. Eventually, after quadrillions of years of star consumption, the black hole could gobble up the Milky Way, all of it. By that time, humanity would most likely be long gone anyway. That is, unless another cosmic event disrupts this feast some 4.5 billion years from now. But that's a story for another What If.
So we know that black holes consume everything that falls within their reach. Yet in the video shown before and in this picture, we can spot like jets of particles that is fleeing from the black hole at nearly the speed of the light. And these particle escapees steal some of the spinning black hole's rotational energy. This is accomplished by through two main mechanisms involving magnetic fields. And these jets of particles are known as the relativistic jets. As a black hole spins, its dense mass distorts and twists the surrounding fabric of space-time in a phenomenon known as a frame dragging. So let's look into a simulation which shows this effect. So the simulation shows that the magnetic fields at the poles of the black hole become coiled and spring outward, flinging jets of particles into the space. At the equator, on the other hand, the magnetic fields collapse into clumps, and this tangling creates areas that act like particle accelerators inside the black hole, and these boost some particles into the edges of polar jets at high speeds and others into the maw of the black hole. However, tracking of these jets is kind of tricky because the complexity of physics involved is like high. However, the black holes, like some of the simulations have been done, like the simulation shown here. Black holes, like they bend space-time and general powerful like magnetic fields, and particles on the outskirts of the black hole zip around the untethered from atoms in a state of matter called plasma. And new particles can pop into existence from this plasma, such as pair creation, which is such as pairs of electrons and their antimatter doppelgangers, such as the positrons. As the simulation progresses, a previously predicted mechanism called the Planford-Zanuck process occurs near the south and north poles. During this process, the black hole twirls the fabrics of space-time, and this distortion in the space-time twists the magnetic fields into coils near the pole, and these coils then spring outward into the space like a jack-in-the-box, extracting spin energy from the black hole and launching jet particles. Near the black hole's midsection, however, a different and an unexpected particle boosting mechanism appears. The magnetic field lines operating in opposite directions, that the magnetic field lines, like they meet together in this section, and this congregation causes the lines to twist and tangle. In the space, these bundles, the magnetic field is like relatively weak compared with the black hole's electric field. Hence, the electric field comes into play, and now it is the strongest force. And these accelerates particles. Some fly outward following a curved trajectory into the peripheries of the polar jets. Others speed into the black hole. And from afar, when you're seeing the descending particles appear to have negative energy, as a black hole eats them, and the black hole loses a bit of its rotational energy in what's called the Penrose process. Overall, the simulation suggests that 80% of the jet's energy, that is the relativistic jet's energy, comes from the corkscrewing magnetic field at the poles, while the remaining 20% originates from the particles accelerating at the equator. Another particle which I came across was the relativistic protons, as these were associated with active galactic nuclei, and it is necessary for these protons to exist for high energy neutrons to come out from the jet. So I will be attaching the PDF following it, so you can just go through it to learn more about these relativistic photons. So the ice cube detector. The ice cube experiment at the South Pole uses a grid of sensors beneath the ice to look for energetic neutrons from beyond the galaxy, and most of the energetic neutrinos were witnessed by these ice cube experiments. Researchers were able to witness neutrinos with peta-electron volts of energy, or 1,000 trillion electron volts. In this particle world, this is a very large amount of energy. IceCube also traced a high-energy cosmic neutrino back to its source for the first time in 2018. So cosmic neutrino, like cosmic events, like large events such as the merging of black holes, they release a large amount of neutrinos as well as cosmic rays, gravitational waves. So when we're able to detect the neutrinos, along with it, these are traveling the speed of light. So along with it, the gravitational waves also will be coming from that source. So using other multi-messenger astronomy, we are able to detect its source. So it came into the part of multiple messenger astronomy. That is what is ushered the neutrinos into the age of multi-messenger astronomy, which uses signals from different kinds of messengers, including the cosmic rays, gravitational waves, and electromagnetic radiation, to study the cosmic phenomenon. Okay, so this is the ice cube of the South Pole. It observed a pair of cosmic neutrinos at energies around, that is the 10 to the power 15 electron volt, which were nicknamed by the ice cube collaboration as Bird, Ernie, as well as the Big Bird. These were after the characters, named after the characters from Sesame Street TV. So this is for Bird, and this is for Ernie, and this is for Big Bang. So these images show the detection by the ice cube strings of detectors of 3 highest energy cosmic neutrinos. And these 3 cosmic neutrinos are named like Bird, Ernie, and Big Bird, and these are named after the Sesame Street characters. However, these were the source of these have not yet been. Okay, so the source of these neutrinos could have been like any of the eruptions of supermassive black holes, or the merging of black holes, or it could be active galaxy as well. So cosmic neutrinos are particularly important because they help in pinpointing rare cosmic events that happen in the universe. These could be the merging of black holes, pulsars, or gamma ray bursts, or active galactic nuclei, or it could be an entirely new type of source that scientists have never seen before. So it could be anything. So with this, we just come to the end of this lecture. We started with the Big Bang neutrinos, from how the neutrinos actually are the reason why we are existing today. And we went through the stellar neutrinos, and we also went to the supernova neutrinos, how bulk amount of neutrinos are created in supernova neutrinos. And we come to a close with the cosmic neutrinos. And this will be the end of the lecture. Thank you.
Very nice presentation, guys. It was so nice today. So, anyone have doubts?
Sagar, I just wanted to clarify that in my LaTeX there was like it was written anti-neutrino. It was anti-neutrino. It was only neutrino. That's what I wanted to clarify.
Okay, in which equation, bro? I don't remember.
It's okay. It's in proton-proton chain reaction on first step. Yeah.
Okay. So, did you all understand, guys? Your cohort mates lectured you, so no doubts in that. Okay, I think you all talked before that. I will not ask you in your class. You don't ask me in my class. Is it like that?
No.
Okay. So it was pretty well. Yeah, it was pretty well presented because all the types of astrophysical source of neutrinos were covered. I think like Big Bang, and then stellar neutrinos, and then finally cosmic. That is through jets. So,
Sagar, can I ask a question, Sagar?
yes, sir.
Yeah, I am not part of the group, so maybe I am asking very fundamental one. See, this neutrino is the only fermion which has no charge. Any thought on that? What makes it zero charge?
Sir, your voice is not clear. Can you please repeat again?
See, neutrino is the only fermion which has no charge.
No charge, yeah.
Charge, the only matter particle. So, any thought why it doesn't have any charge? Any thoughts on that?
Any thoughts why it's not having charge? Is it?
Yeah,
Is it that?
why it does have a charge? The only matter particle without charge.
So can anyone answer, guys? Why neutrino is the only matter particle, that is the fermion, which has no charge?
First of all, like neutrino is a lepton. I think it's not a fermion. And
bro, what you're telling? Leptons are fermions, right?
Neutrino or neutrons? I'm sorry, I'm confused.
Neutrino.
Right now, neutrino is the only fermion which has no charge. Rest all.
Yeah.
Everything has charge.
I guess quantum field theory might have charge.
Okay, how quantum field theory helps, Hatila?
Yeah, that I don't know actually.
Maybe it's because of conservation of charge.
Okay, maybe you can put that in Discord. Can I ask one more? I don't know actually because because of the time difference I couldn't be part of the project. Because it's from 6 o'clock and 6:30. So sorry for that. Just another one. Sagar, can I ask? Hello.
Yeah, you can sir.
Yeah. You see, somebody said very rightly that neutrinos are the next most particles after photons in the universe. Right? That's right, I think. Is that correct?
Yeah, they are most abundant.
Abundant after photons.
Not after photons, actually more than photons maybe.
More than photons?
Yeah, why? Because
second to photons. No.
Okay.
Photons are more.
Okay, fine. Whether it is more or less, okay, that's because I heard somebody the first person who talked these days is the next abundant after photons. Okay, but if you compare photons and neutrino, see the one is I think both travel almost neutrino travel at the almost same as the speed of light, but it has some mass. It has some rest mass, whereas photon has no rest mass. So the total energy in a neutrino, in a quanta of neutrino, should be more than that of photon. A quanta of neutrino should have more energy than of a photon because this has the same speed, almost the same speed, whereas it has some rest mass, whereas photon has no rest mass.
Yes, sir. Yes.
Now, if I am not, if I am asked something very strange, sorry for that.
Can anyone answer, guys?
I don't know the exact details, but I think he's right. I mean, they have some rest mass, and when you even if you speed them up, they will have more energy, I guess.
I was having a similar kind of question. Is there any limits? Like we have limits of the speed that it can be greater than the speed of light. And there be any limits on the other physical things like energy and all?
We can actually relate this limit of speed to the limit of energy, right? Because if you consider a particle has energy half mv square, there we should not be greater than c, so we'll get the limit for energy also. One idea.
Yeah, but not for a certain particle. The absolute limit I'm talking about. That energy can be greater than this quantity.
Okay. Can anyone answer, guys? I know the answer, but you guys try answering that.
I think it depends on the particle, like what mass it has. Then only it has some limits of energy, I guess. I'm not sure about if there is any limit of particular energy of all the particles. I think it depends on the mass of the.
I'll tell you what I'm thinking. What's the direction of my thinking? Somebody just told, even neutrinos may be more than photons. The photoelectric effect, that the electricity we are generating mainly because of the photons are able to eject. So I was just thinking if a neutrino has more energy because of his rest mass plus equivalent like speed of light like photon. So whether we can think of a similar type of photoelectric effect for neutrinos. That is the thing I was in my mind. That's why I was asking you a quanta of neutrino whether it has more energy than a quanta of photon. If that is so, then whether it can be used like the photoelectric effect in the photon type. That's the way I was thinking.
Okay, sir. So I don't think your question was answered because I think nobody knows to your level, but it's fine now. So we'll try finding out the answers. And more, sir, if you can you post the answers in the chat box so that we can use it in future? I mean, post the questions. Hello. Guys, am I audible?
Yes, Sagar.
Okay. Okay, let's. Okay, anyone else have any questions or doubts? No.
Yeah, I didn't get the answer. You said you know, but you don't give one.
Actually, there is no limit for energy as such because if you consider energy of a body, like consider the energy of me. If you see the energy of me, it is my mass into energy c square, right? there is no limit for that. Consider a mass with a particle which is having more mass than me. Like consider a mountain. If you see the total energy of it, it has energy E is equals to mc square. There is no mass limit for that. So there is no energy limit also. So I don't think there is an energy limit as such. Consider only for particles we can tell, like for maximum energy that an electron have, I can tell that.
Yeah, that
Maximum
we can
energy.
tell that by comparing it with its speed. Yeah.
But I can't tell maximum energy that all particles can have at once.
Okay.
Okay. So one more question was why neutrinos are the only fermions which have no charge. So actually we had one full week dedicated on quantum numbers. You should have been known why there is no charge. So how is charge defined for leptons? Can anyone tell? There's an equation also, right? I is equals to half into isospin. Remember?
Yeah, it depends on the isospin. Yeah.
Yeah, but for all particles, the net the net equations give plus or minus one, or for leptons plus or minus one. But for neutrinos, it adds to zero. So neutrinos have no charge. But why it is happening? Why the quantum numbers of neutrinos are such that the net electric charge becomes zero? That I also don't know. We have to learn more on gauge theory to come to know that. But according to the equation, it is zero. But why it is according to that equation, we don't know still. Okay. So one small change in the Tuesday's quiz thing, that is, I asked each person to give one question, right? I'll instead of one question, each person can give maximum 3 questions. You can give either 2 or either 3. It's up to you. Okay. 2 questions is okay, or 3 questions is okay. You can give 2 questions or 3 questions, but not more than 3. Okay.
Okay.
Okay, guys. So